So in the last class, we have discussed about non-stationarity, and we have mentioned non-stationarity means a series containing trend. Two types of trend: deterministic trend or stochastic trend. And also we have discussed about the concept of unit root, and we have mentioned unit root is related to the concept of characteristic roots of the characteristic equation. So if the characteristic roots of the AR characteristic equation equal to 1, then we can say that a series contains unit root. Okay. So the presence of unit root, if a series contains unit root, we can say the series exhibits stochastic trend. And alternatively, we can say a series with unit root is a series following random walk process. Random walk process is a very much important process that is observed in many time series, particularly financial time series. Random walk process is simply AR1 process, autoregressive of order 1, where the coefficient of yt minus 1 is equal to 1. So it was phi 1 in our previous day's analysis. So if the value of phi 1 is equal to 1, your model looks like this. So if a time series yt behaves in this way, that is yt, value of y in period t, is equal to some constant plus value of y in one period back plus current period shock, then yt will follow a process what is called the random walk process. So random walk process is similar to the unit root process. Okay, because random walk appears when a series contains unit root. And if you manipulate this equation, it is a first order difference equation with stochastic component. So it is called a stochastic difference equation of order 1. So if we solve this stochastic difference equation of order 1, we have a time path like this. So this is the value of yt. So this and these are similar, but it looks like different. So this is the original process. Value of y today is equal to certain constant plus value of y yesterday plus today's shock. And we can express the same process in this way. So value of y today is equal to, it has two components. This is the first part. First part looks like a linear trend, y naught plus phi naught into yt. Y naught is the initial value of y. Phi naught is this is called the drift element in time series literature. Drift or the intercept term. So this into t. So yt increases over time at the rate phi naught if it increases, or decreases over time at the rate of phi naught, plus there is another component, sum of epsilon. So this sum of epsilon means the shocks are accumulating. So by the accumulation of this shock, another kind of trend appears, what is called the stochastic trend. So if yt follows this kind of behavior, so it will contain two types of trend together. One is the deterministic trend. It moves upward or downward, that is observed by looking at the time path of the series. And another component relating to the accumulation of the shocks, and it actually reflects the trend component in the variance. That is, if shocks have been accumulating over time, then the variance of the series will follow certain kind of trend. Okay, so if a series following AR1 with unit root, or if a series follows a random walk process, then the series will contain both kind of trend, deterministic trend, stochastic trend. As deterministic trend is observable, we can easily tackle with this kind of trend. But this part of trend is not observable. So it is highly difficult to tackle with this kind of trend. That's why in time series analysis, we are more concerned about this component, sum of the shocks, sum of the random shocks, okay, or the nature of the stochastic trend. And the nature of the stochastic trend can be analyzed in terms of the behavior of unit root. How many unit roots presents in a series? If the number of unit roots different, the pattern of stochastic trend will be different. So for that purpose, we need to carry out unit root test. Okay, whether a series contains unit root or not, for that purpose, we have to carry out a formal test, what is called the unit root test, and we will discuss how to carry out unit root test later on. And most of you know, unit root test actually developed by Dickey and Fuller in 1976. So unit root test started with the Dickey-Fuller test. This is a classic test, and later on this Dickey-Fuller test is developed in different way to capture different complications appeared in the data. So this part will be discussed later on. So before going into the unit root test, let we try to understand the possible types of stochastic process a time series may follow. That is how we can express the behavior of a time series, or how we can specify, how we can develop a time series model, univariate model. Univariate model means we are considering only one variable. Look at this model. So this is a univariate time series model. We are considering only one variable, y. So value of y today as a function of value of y yesterday. So the variable is the single variable for different time periods. Okay, so in a time series data, we can develop or we can specify a univariate model. But this kind of univariate model is not possible with cross-section data. If you have a cross-section data, you cannot estimate a model like this. Y is equal to phi naught plus y plus epsilon. So this is the univariate model, and univariate model is estimable only if you have a time series data. So univariate model may also be of different types. So here YT follows one kind of behavior. What is the type of behavior here? Y today depends on the Y of the past values, etc., etc. So if Y follows this kind of behavior is popularly known as autoregressive process. Okay, so you have a data. Your data may follow either autoregressive process or moving average process or autoregressive moving average process or autoregressive integrated moving average process. So there are 4 possible stochastic process a particular time series can follow. Okay, but you don't know beforehand. You have a data only. So you have to have some idea about the behavior of the data you have, whether your data follows autoregressive process or moving average process or autoregressive moving average process or autoregressive moving average process with some integration. Okay, so this is the first task for time series analysis. So you have a data, so you have to know whether your data will follow AR process or MA process or ARMA process or ARIMA process. If it follows AR process, you can think about the behavior of your data in this way, what we have discussed in the last class. Okay, but if your data follows MA, moving average, then the type of analysis of your data will be different. If your data follow ARMA, type of analysis will be different. Okay, so the first task or step 1 is to find out the behavior of the data or the data generating process, whether the data generating process follow AR or MA or ARMA or ARIMA. Okay, now we can express AR process summarily in this way: ARP, autoregressive of order P. ARP means AR autoregressive. Autoregression, we have defined autoregression means self-regression. That is, we are regressing Y on Y, current value of Y on past values of Y. For that reason, this model is called autoregressive model. So how do we determine order? Order P. Order P means, just look at this equation, Have you seen this clearly, or can we zoom it more? This equation, it is clearly visible to you? Okay, so
Yes, sir.
okay. So here we have specified value of y today, value of y in period t depends on value of y in period t minus 1, period t minus 2, up to period t minus p. So we are considering the back value up to period p. So this p is called the lag length. Okay, and this lag length will determine the order of autoregression. So if this model is valid for a particular data, particular variable y, then y will follow autoregressive process of order p. Okay. Now for analytical purpose, we can simplify the expression of this process. So if we look at this equation, this is simply a difference equation. Difference equation with stochastic element epsilon t. So autoregressive process is specified mathematically in terms of a difference equation with some stochastic element epsilon t. So we can solve this difference equation. You know how to solve this difference equation in a linear algebra, but the complication appears here because of the presence of epsilon. You are familiar with the difference equation without epsilon. Okay, and hopefully in your undergraduate you had in your syllabus up to second order difference equation like this: first order linear difference equation, second order difference equation. So you know how to solve second order difference equation. There are two components of the general solution. One is the particular solution representing the stationary part. Another was the complementary function representing the solution for the homogeneous part. Okay, and by adding them, we have got the general solution. And because of the presence of the stochastic part, we have another component here. So if we solve this stochastic difference equation, we have three components. One is the particular solution representing the stationary part. Another one is the complementary function or homogeneous solution. Third part is called the challenge solution. You don't know, you don't need to know in detail for the time being what is challenge solution or how do we solve this kind of difference equation. Just keep in mind, if we solve this difference equation, we have three components in as a general solution. One part is the particular solution, another part is the homogeneous solution, the third part is the challenge solution. If you are interested, you can go through the literature, you can go through the books to look into how we can solve this kind of equation. And hopefully you can find in chapter 10. I have provided you chapter 11 for understanding what is non-stationarity, how do you carry out unit root test, etc., etc. So before it, to analyze the autoregressive behavior, you have to go through chapter 10 of the book, or any standard econometrics textbook you can follow, no problem. Now, to simplify the expression, you can use the lag operator. We have mentioned lag operator in the last class. How do we define lag operator? Just look at this expression. Yt minus 1 is equal to Lyt. Okay, so L make a relationship between current value of y and past value of y. Similarly, we can express Yt minus 2 is equal to Lyt minus 1. Clear? If we substitute the value of Yt minus 1 from the previous expression, you have L of Lyt, that is L square Yt. So you can write Yt minus 2 is equal to directly L square Yt. In this way, you can write Yt minus P is equal to L to the power P Yt. So if we substitute the value of Yt minus 1, Yt minus 2, etc. up to Yt minus P in terms of the lag operator, you have this kind of expression. So what is the difference between the original expression and this expression? In the original expression, in the right hand side, you have Yt minus 1, Yt minus 2, Yt minus P. In this expression, we have converted all lag values into the current value, yt, 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 along with the lag operator. Okay, so if we take all yt in the left hand side, you have got the expression like this. তোমরা খাতায় একটু ডেরিভেশন গুলো একটু করে নাও, খুব সিম্পল ব্যাপার, তাহলে বুঝতে পারবে, শুধু মানে কথা শুনে বুঝতে পারবে না। এখান থেকে এটা কি করে আসছে জাস্ট একটু দেখে নাও। Okay, so you can take yt as a common factor and you have an expression like this. 1 appears from this term, and if you take the rest of the y from the right hand side to left hand side, so the sign will be plus converted into minus. So 1 minus phi 1l minus phi 2l square up to minus phi p l to the power p into yt is equal to, in the right hand side, phi naught plus epsilon t. Now this expression within bracket is called the polynomial, AR polynomial or autoregressive polynomial of order p. As in our model autoregressive of order p, we have a autoregressive polynomial of order p. Okay, now for simplicity, suppose we denote this polynomial as phi of l. So phi of l means phi of l is equal to this 1 minus phi 1l minus phi 2l square minus up to phi p l to the power p. Okay, now if you set this polynomial equal to 0, you have an equation, what is called the inverse characteristic equation. And in this inverse characteristic equation, if you set 1 by L is equal to Z, you have what is known as the characteristic equation. You can solve this characteristic equation. So you have got the values of roots, characteristic roots. So in this case, if your data, if your variable follows ARP, you have pth order characteristic equation. So you have p number of characteristic roots by solving this equation. Okay, and if sum of the roots equal to 1, then we can say this autoregressive process will contain unit root. So in the ARP process, when all roots equal to 1, so how many roots you will get? You will get maximum p number of roots. So if all roots equal to 1, then the series will contain p unit roots. If p minus 1 number of roots equal to 1, the series will contain p minus 1 unit roots. So in this way, we have different possibilities. So number of unit root may be equal to 1, equal to 2, equal to 3, equal to up to p. Okay, and if a series contains unit root, then we can convert the series into a stationary one just by taking difference. So if a series contains 1 unit root, we need to take first difference to make it stationary. If the series contains 2 unit root, we need to take second order difference to make it stationary. And the number of unit roots present in a series determines the order of integration. So if this series contains p number of unit roots, this series will be called integrated of order p. If this series yt contains only 1 unit root, then we can say this series is integrated of order 1. For 2 unit roots, integrated of order 2. Why we call the series integrated if it contains unit root? Simply because for estimation, you need to convert the non-stationary series into a stationary one. To convert it, you have to take a difference. So after taking difference, you have estimate the model. After estimating the model, you have got the meaningful estimated values. But originally you have a non-stationary series. So you have estimated a difference values. So to reach at the original one, so you have to convert the difference equation to original equation. So just by taking integration. So how many times you need to integrate it? That depends on the number of unit roots. If unit root is equal to 1, you have differentiated once. So to reach at original, you have to integrate 1. If the number of unit roots 2, you have differentiated twice the series to make it stationary. So to reach the original one, you have to integrate twice. So integrated of order 2. So in this way, if a series contains d unit roots, you need to take difference d times to make it stationary. So in that case, we call the series is integrated of order t. Okay. So this is about the autoregressive part. Similarly, if a series follows moving average series looks like this. Just try to understand the nature of the moving average series. Y is your data. Yt is equal to epsilon t plus theta 1 epsilon t minus 1 plus theta 2 epsilon t minus 2 in this way. In other words, for moving average series, current value of y depends on current period shock as well as the past period shock. So in this case, y depends only on the shocks or the errors. In the AR process, y depends on its past values along with current period error. But in the case of moving average process, y the variable you have completely depends on the errors, current period error, past period error, etc. So if a series behaves like this, we can call the series as a moving average series. Sometimes, or in many cases, the time series you have may follow the mix of autoregression and moving average. So if a particular series follows both autoregressive and moving average, then we can call the series will follow ARMA, autoregressive moving average of order PQ. So first component P denotes the order of autoregression. The second component Q denotes the order of moving average. So if you look at the expression, how do we express ARMA series? So Yt is equal to phi naught plus phi 1 Yt minus 1. In this way, up to phi p Yt minus p. So up to this part, this is autoregressive. Then we have the moving average part, epsilon t plus theta 1 epsilon t minus 1 plus theta 2 epsilon t minus 2 plus, in this way, theta q epsilon t minus q. In compact form, we can express the series in this way. Phi of L Yt is equal to phi naught, the intercept term, plus theta of L epsilon t. What is theta of L? Theta of L appears in this way. This is the moving average polynomial. So if we introduce lag operator into the error component, you have a similar kind of polynomial in the moving average, and we can denote this polynomial as theta of L. So this theta of L is called the moving average polynomial. So in the case of ARMA, you have two types of polynomials. One is the autoregressive polynomial, another one is the moving average polynomial. So for analyzing stochastic trend or the non-stationarity of a series, we have to focus more on the autoregressive polynomial part, phi of L, not on the theta of L. Okay, why? Because if you look at the moving average behavior, Yt depends on epsilon. And by assumption, epsilon is stationary. Just think about the assumptions we need for a linear regression model. Mean value of epsilon 0, variance of epsilon constant, covariance 0, etc. So epsilon always stationary. So if a series y follows moving average, then the series will be stationary always. Okay, so moving average series will not be non-stationary at all. So non-stationarity appears only in the autoregressive part. For that reason, we need to concentrate more on the autoregressive part to find out whether the series contains unit root or whether the series exhibits stochastic trend, etc. Okay. Now, when this ARMA series, ARMA conventionally is considered as a stationary one. So if in an ARMA series there are unit roots, then this model will be called ARIMA. So what is the difference between ARMA and ARIMA? ARMA is stationary, but ARIMA is non-stationary. So non-stationary ARMA is called ARIMA, autoregressive integrated moving average. The term integrated appears because of the non-stationarity part, because of the presence of unit root. So if a ARMA process contains unit root, then we can say the series will follow ARIMA. Okay, so these are the 4 possible data generating processes we have to keep in mind, and how we can express this data generating process. You need to remember the expressions. For moving average part, we can express moving average in this way. For autoregressive part, we can express autoregressive part in this way. For ARMA, we can express in this way, etc. So for further analysis, we need to know the basic expression of ARMA, AR, MA in this way. Okay, so we need to switch on the next class. We have a time, just a minute. We have a time less than 1 minute, so it will be disconnected automatically, and I will provide you the another link to join the next class for further analysis. Okay, bolo.
Sir, ARMAটা কেন স্টেশনারি একটু বুঝিয়ে বলবেন স্যার?
আর্মাটা স্টেশনারি কেন